Welcome to this presentation about Kueue. So what is Kueue? Kueue is a job queuing and quota management system. It's virtually inserted just before the Kubernetes scheduler, and it is in charge of when a job is submitted to decide if it should be admitted for scheduling or it should be deleted in case of resource scarcity based on queue management. So how does it work basically? I was mentioning like when a jobs pop up. So what happens normally is that Kubernetes will just like take this job and it will create the relevant pod. But to make Kueue be able to work, we need to enable a feature gate, which is suspend job. So every job that will be submitted into the Kubernetes cluster, it will be suspended, and this is where Kueue will start to work. So normally the job controller will watch the job, and then Kueue will be notified about the job creation. Kueue will then create a workload object defining a pod set, which is basically a group of pod that the job will be bringing, and it will also determine the resource request and resource limits. The job, when it is submitted to Kueue, it also holds the name of the local queue where the workload will be submitted, and this is how Kueue will determine where to place the job, but we'll go into detail with that within the next slides. Once the workload decides in which potential node it will be assigned, it just delegates the scheduling of the pod to the Kubernetes scheduler. And finally, the pod gets created into the relevant Kubernetes node. So how does Kueue really work? It's quite simple. It relies on a few basic concepts that we'll go into detail right now. So the concepts that we will look into detail are resource flavor, cluster queue, cohort, local queue, workload, and jobs. And an additional concept that we will see, which is the workload priority class. So the first concept is the resource flavor. So a resource flavor is a kind of super label that allows you to group Kubernetes nodes based on labels, taints, and tolerations. So when you create a resource flavor, you define the node labels that the resource flavor will select. When you define the resource flavor, you can specify a set of node labels, and all the nodes that match these labels, they will be grouped within this resource flavor. The next important concept is the cluster queue. So the cluster queue is a cluster scope object, and usually this is defined by the ROI admin persona. A resource queue has access to resources, and these resources are brought by the attachment of resource flavors. So you can attach several resource flavors within resource groups that lives inside of the cluster group, and this will give access to the cluster group to these specified resources. Also the cluster queue defines the quota of every resource. So we have a specific field, it's called the nominal quota, and the nominal quota gives the minimum amount for a specified resource that can be used or guaranteed to this cluster queue. Cluster queue can also be grouped within cohort. So when there is underutilization of resources, the cohort system allows like borrowing of resources between cluster queues that belongs to the same cohort. One cluster queue can only belong to one cohort, so it cannot belong to several cohorts. And in the same cohort, they can borrow from each other unused resources based on quota. And of course, there is like some priority and preemption that can happen, and we will go into detail for that within the next slides. Okay. So the next concept is the local queue. So the local queue right now, it's a namespace scoped object, and this can be created by queue users or job submitters, I would say. The local queue, a local queue is linked to exactly one cluster queue. So if you have like one local queue, you will specify which cluster queue it will use. And this specified cluster queue determines for your workloads in which cluster queue they may land in terms of resource usage. So what is a workload? We have seen previously that when a job is submitted, there is a workload object that gets created by queue. There are different types of jobs that are supported by queue. So the batch v1 job, which is basically the classical scheduling, the classical Kubernetes job, but some other type of jobs are supported, like ray jobs or classical pods or deployments and so on. And yeah, the list can be expanded in future versions of queue. A workload is the unit of admission in queue. It will contain the local name, the local queue name. So as I mentioned, a workload will be attached to only one queue, and so as it is taken from the job description, this is held by a label, a specific label that queue will read from the pod, from the job, and it will create the corresponding workload with the same queue name value. And also, it will gather the resource requirement for the pod. So based on the requirements defined in the job, it will also extrapolate the resource request and resource limit for for all the pods that are defined within the workload. One small remark: workloads are not intended to be created by users. They are created automatically by the queue controller, and they can. So one small remark: workloads are not intended to be created by end users. They are created by the queue controller automatically, and they syncs the decisions and statuses for each object. If you want to have a big picture of how things work, the first step is when a job is submitted. This is here. The job controller in Kubernetes will be watching that and notify this. It will create the relevant object into the API server. Then the queue controller will get the information by watching the API server. The queue controller will then create the relevant workload and attach it to a local queue based on some scheduling decisions. So it may depend on the available resources, the quota assigned to the cluster queue, etc., etc. And then based on the cluster queue attached to the local queue and the resource flavor that will be matching the requirements for this workload, the node destination will be assigned, and this will be delegated to the scheduler, who will decide where the pods will be scheduled. Let's continue now with the demo of queue. So in this demo, I will show you the different concepts that we have discussed in the previous presentation, and I will illustrate them through a demo. So to do that, I have created the different type of resources in these different files. So the first one contains, for example, the resource flavors, the workload priority classes, and the second one contains the cluster queues and so on. To make it more visual, I also created a dashboard. It's called QVs that we will use to watch this different type of resources. So let's create the first one, which are the resource flavor and the workload priority class. So the default flavor here is the one that we'll be using for our demo. it doesn't have anything specific into its spec attribute. So basically, it's the default flavor, and it will capture all the nodes that are present in our cluster. The second type of object that we will create are the cluster queues. These one are the most important if in our demo. The cluster queues, they are attached to one or multiple flavors. In our case, they will be using the default flavor, and they have the ability to belong to a cohort. So a cohort, as we have mentioned, is a group of cluster queues that can share resources in case of scarcity. And the first part of this view here illustrates, gives details about how this sharing is happening. So the first part, which is the flavor fungibility, tells that this queue, the emergency cluster queue that I have configured to be the most aggressive in terms of resource borrowing. So it can borrow resources from other cluster queues in the same cohort, and it can also preempt workloads based on some conditions. And so these conditions are defined here in the preemption settings sections. It can reclaim within a cohort any workload. So if there is another workload running on cluster queue that is using, for example, resources that have been borrowed from the emergency cluster queue, the workload that is intending to run on the emergency cluster queue will be able to preempt the other workload in favor of himself. Then it can also borrow within the cohort resources if they have if the workloads that are in competition for these resources have a lower priority. And within the same cluster queue, it can preempt any workload with a lower priority for a given workload. Then here in this section, we define the quota or the resource groups that are used or allocated to this cluster queue. So we can have like different quotas based on different flavors, but in this case we have only configured one flavor, which is the default flavor. And for this cluster queue, we will have like one CPU and 2 gigs of RAM. And for the memory, we give the ability for workloads to borrow up to 500 megabytes of memory from cluster queues within the same cohort. The last part of the view is empty right now because it shows the live usage of the cluster queue, and right now it's not used because there is no workload running into our queue cluster. The almost last step is the local queue. So the local queue are linked to one and only one cluster queue. I'll just show you how it does look like. So basically we have defined the 3 queues, and we define which cluster queues they will be attached. And it's very simple here. There is nothing special for that part. And finally, we will go for the workloads. So for the sake of the demo, I have created 2 types of workloads. The first one will be the LLM workload, which is a fake training of a machine learning process. It will require 50 millicore of CPU and 50 megabytes of RAM, and it will run 3 pod into its pod set to run this processing. So let's try to create a few of them right now. And as you see, as there is enough resources, they are all able to be created and admitted into the cluster queue that their local queue is targeting. And what it means that all the pods specified in the pod set will be also started and passed to the scheduler to be scheduled in the Kubernetes cluster. If we have a look at the cluster queue here, we will see that the flavor reservation and flavor usage have moved. So now for the CPU, we are reaching 750 millicores of CPU. That's the 500 nominal quota plus a certain amount of borrowing, 250. And for the memory, it's the same. We have 750. That's 500 megabytes of memory plus 250 from borrowing. We are almost at the limit. So what happens if we create another bunch of LLM workloads? So here we can have another one that gets created, but if we create another one, then we are reaching the maximum resource usage of the queue, and so our workload cannot get admitted until there is enough resources that get freed. Okay, so now let's create another type of workload. The one that we will be using now is the queue cancer job, and this one is using a different queue. It's using the emergency cluster queue. So it's hitting another pool of resources. So we have created 3 pods of 50 millicore of CPU and 50 megabytes of memory each. So that's using this amount of memory. And if we create another bunch of them, for example, these 5 new workloads, we see that the usage is increasing. Okay, and if we create another 2 more, what will happen here in the dashboard? It will be visible. Then we get some pods, some workloads that even get evicted in favor of these new workloads that are more priority, that have higher priority. So these workloads, they were waiting before, they were running, I mean, or they can also be waiting, but a workload with higher priority came, and it's written here in the message. So for example, it is this workload. It is Kueue cancer workload job. And we can see that first it wasn't able to be assigned because of insufficient quota, but then there was a preemption that happened, and it was waiting for the preemption. When the preemption happened, the workload has been admitted to the cluster queue emergency queue. That's all for the demo, and thank you for watching that.